what is thinking fundamentally? Can anyone give me a definition?
To fundamentally think.
What does that mean for a crisp definition? Yes?
To think logically?
To think logically? Okay. Yes?
To think about the basics of something?
I like that. That sounds good. Think about the basics of something. Come after class if you ever can. So, to think fundamentally, I think, is to sort of simplify how we view the world. And from that, we can go ahead and lead us to some pretty cool conclusions. Let me just go ahead and make sure the sound is on. Cool. So yeah, it'll lead us to some pretty cool conclusions. So, let's take a look at this. So can someone describe to me what's going on here? Yes.
There's a fire tornado.
Okay.
There's a fire and there's a bunch of fans put around it and angles toward it. It's like a fire grows with oxygen, so the fans are pulling the air which has a lot of oxygen in it towards the fire, which increases the fire.
It's wind and fire.
Yeah. I like all those descriptions. So but how exactly can we sort of think about what we saw like more simply? Like we're talking about the basics. We really want to understand it from a basic perspective. So in order to do that, we have to like think about 4 key ingredients to life. And I claim that those are matter, what things that are what it's made of. Gravity, we deal with gravity every day. Light and energy. So we'll start off with matter. So who can answer this question? Yes? Atoms? I'm sorry? Matter. Molecules? All the above. I think it's all the above also. Because everything we have, I have this laser pointer, I got this wrench over here, it's all made of, molecules. And everything around us is made of molecules. So atoms are matter, they're molecules, everything matters. Gas, solids, liquid, plasmas, the different states. So, matter makes up everything. Matter makes up everything, and as you guys know, matter contains electrons, contains protons. But in order to think about, matter more fundamentally, I think we should forget about this idea of electrons and protons and just think about atoms in terms of little balls that are connected by a spring. And sometimes I can squish these 2 balls together, sometimes I can pull them really far apart, sometimes I can break the spring that holds them together. And whenever we want to think fundamentally, we really should focus on, we don't want to use like huge words that we have to take a long time to explain. We want to try and just like think about basic concepts. So these, like I said, these balls can be squished, they can move, they can go left, right, up, down, forward, back, they can interact with each other, they can jiggle. That's a very important part. So let's just keep this in mind as we move forward. And if at any point you guys have any questions, feel free to shoot your hand up, I'll be happy to answer it. So, what would you guys say about each of the stages here? Someone raise your hand, tell me a little bit about A, someone know, and tell me a little bit about B, yeah.
Looks like solids, liquids, and gases to me.
Okay, yeah, that seems reasonable. I would say we don't necessarily know for sure, but I think that's pretty reasonable.
In A, they're more squished together, and B, they're a little more spread apart, and C, they're all stretched.
Yeah, I like that. I like that because what this person just did was to say, okay, I know a little bit about the fundamentals. I have these balls and they're connected by a spring. In this state, they're super tight. So they can't move around. They can't roll over each other. In this example, they're a bit more loose. They can move a little bit. In the last example, they're free to move around. They have they're very excited. They said, I don't want to be next to my friends. I want to be on my own. They're like little happy atoms, little happy balls. So we could describe them as, in this state, this sort of more gaseous state, we can say that they're less squished and there's more movement. Whereas in the more solid state, things that we see every day, tables, floors, chairs, things like that, it's more squished and there's very little movement. And that's why when I take this ruler, I try and bend it, it doesn't really move too much. If I take this water and I want to pour it, it'll go everywhere. Because in this example, the balls, they're super tightly packed. But in this one, they're actually a bit looser, so they can move around. So what would you say like each one of these is in terms of this, this here? Yes? One, just one. Just pick one and then tell me.
I think A is the table because
is the yogurt. Okay, why do you think that is?
The yogurt's a little more loose.
Okay. So do you think, I agree with you. I agree with you. Now, okay, let's have one more person. Yes.
I think the middle one's C.
Okay. And then, so who can tell me what would happen if I took B and I put it in a freezer? Yes.
Freeze, and the parts of probably HA.
Okay, so what does it mean to freeze? If something freezes. Yes. Okay, so think about it from like the yes.
All the balls would start to slow down, they wouldn't move as much, and they start to compact and look a little more like eggs.
Exactly. I'm gonna grab a candy after class. So yeah, so that's exactly what will happen. And we'll talk a bit more about this idea of energy and how it can change how these balls are positioned in objects. So let's think a little bit about liquids and gases. I think this is a really, really interesting thing to think about. So I have this cup right here. Let's say there's a bit of water, but let's say there's no water in it, it's empty, and I'm holding it up. Who can tell me what's inside the cup? Yes. Air. Okay. And what comprises it? What's in air? Yes.
It's a lot of different types of gases.
Okay.
So like water vapor.
Sure. Yeah. Definitely. Yes.
Little balls.
Exactly. See, come grab a candy after class. So we have different gases which are inside the cup. You could think of them as just little balls, millions and millions of little balls inside here. Now, how about what's around the cup? Yes.
More little balls.
Exactly, more little balls. So we have little balls in the cup, we have little balls outside the cup. Now what happens when I go ahead and I pour, let's say I'm a bit thirsty, and I fill this up with water. Oh, I just gave it away. What would you say is in the cup now? Yes.
Water. Little balls of water.
Exactly, little balls of water. And what's around it?
Little balls of air.
Little balls of air. Okay, yes. Do you have a question? Okay, great. So now what would you say? Let's say I put this cup and I completely submerge it in here. What would you say is in the cup? Yes.
Little balls.
Of?
Water.
Okay, and what would you say is around the cup? Yes.
Little balls of water.
Little balls of water. So let's think about what we just did. We said, okay, we have this cup. I have little balls of air all around it and little balls inside. I have this cup over here. There's little balls of water around it and little balls of water inside. Can you guys see the similarities between the two? It's kind of interesting. But what makes water different from air? Yes?
Little balls are closer together.
Exactly. Come grab a candy after class. So, what does that mean? Let's say I have an object. I have a little dice here. And I want to move it in the air from this point to this point. Let's think about what's happening. Let's just slow it down in our brains. As I'm moving it, there's millions and millions of little balls of air coming in contact with it. Do you guys see that? So what happens if I do the same thing in water? I move it. There's millions and millions of particles of water hitting this thing. And like you said, the difference is, in this one, the balls are more tightly packed, but in this one they're less tightly packed, which means I can do this much easier than I can do it in water. If you guys have ever taken your hand in a swimming pool and try and lift some water up versus like you're just waving to your friend, there's a big difference. And that's kind of interesting to think about. It's all a matter of how tightly packed the balls are. So something that comes up, so this is a cool little example. So someone explain to me what's going on. Yes?
Someone's shooting a gun.
Okay. Can someone go a little bit more into detail? Yes.
Somebody's shooting water under. Somebody's shooting a gun underwater.
Okay.
The bullet is moving through the moving through the ball of water.
Yes, I like that answer. Okay, come grab a candy after class. So if we think about it, as the bullet leaves the gun, it starts coming into contact with all these little balls. But what was it that you said earlier about the balls of water with respect to the balls of air? They're more densely packed. So what does that mean? That means it has to fight a lot more. So if I did the same thing in air, and I shot a gun here, what would you say happens?
It would go a lot faster.
I'm sorry? Exactly. It would go a lot faster. We got some candy after class. But can you explain to me why?
Because since the little balls are less tightly packed, it can get through them easier.
Yes. It'll come into contact with them, they'll knock it off, and it has less balls that come into contact with it. Yeah. So this is thinking about the fundamentals. It's kind of interesting to think about. Like we started off with this idea of little balls, and we're able to describe how, why my hand can move very easily in the water, very hard in the water versus very easily in the air. It's kind of cool to think about. So now imagine, I take this and I drop it. It fell kind of quickly. But imagine what happened. I go ahead and I drop it in this cup of water. Do you think it's gonna fall? Let's say that let's just think about, I drop it this distance, and then I drop it in here. Do you guys think it's gonna fall faster or slower? Slower. I thought that was a pretty good observation. So it fell slower. Can anyone explain to me why? Yes. Yeah, there's a resistance kind of. Are you guys familiar with like the concept of resistance? Cool. Say it? Yeah, so it's like a resistance kind of. And this is where the idea of air resistance comes in. Or, in this case, water resistance. So as you're trying to move something through a different, through the balls, we think about it, like our world of balls around here versus our world of balls here, there's a different amount of resistance that an object feels. So how about here? So let's say I took a bowling ball, I took a feather, and I dropped it at the same time. What do you think is going to hit the ground first? Yes?
The volleyball,
And why do you think that is?
because it's heavier.
Okay.
I think they're both gonna hit the ground at the same time.
Okay.
Bowling ball, because they're like more tightly packed together and they don't have much space to move around.
The bowling ball, because it has a higher mass and the gravity is dependent on the mass.
Yes.
Because the training balls in the bowling ball are tightly packed together and solid.
Okay. So I think we're getting somewhere. So let's first go ahead and watch this video. This little clip. So first off, who says the bowling ball's gonna hit first? Who says the feather's gonna hit first? Who says they're gonna hit at the same time? So it looks like the bowling ball hit first. Can anyone tell me why? Yes, you.
It has more mass and the little balls are more dense.
Okay, so let's say for this specific example, let's assume, it is known that gravity is dependent upon the mass of an object. But let's assume that gravity is constant, because it's about constant in the regime that we're dealing with. But now, can you give me another explanation why it would be?
Well, the bowling ball is more streamlined, and the
Okay.
feathers have a little more area.
I like where you're going with this explanation. Can someone expand on that? Yes.
The feathers have a bigger surface area,
Okay, and what does that mean exactly?
so there's more little balls of air pushing against it.
Exactly. Can we candy after class? Both of you guys. That's exactly what happened. So, what would you guys think would happen if I took a vacuum? You guys know what taking a vacuum means? Can anyone explain what pulling a vacuum means? Yes.
We remove all the matter.
Matter. Okay.
Remove all the little balls of air.
Okay. I like that definition. You remove the balls of air. So, can anyone tell me what do we predict is going to happen if we pull a vacuum, we remove all the balls of air? Yes.
They hit at the same time.
They'll hit at the same time. Let's see if that's true. So this is sort of the example. Looks like they're moving at about the same speed. Pretty cool, huh? So based off just this idea of little balls, we were able to understand what's going to happen if we pull a vacuum and we drop two different mass objects, which is kind of cool. Any questions so far? Yes.
I heard that they did it on the.
Yeah, they did. They did it with a hammer and a feather, I think. It's a really cool video on YouTube if you guys, I'd recommend checking it out. But it's a very similar experiment that they're doing here. So this brings us to the next concept of gravity. Can anyone explain to me what gravity is? It's kind of a hard concept, I think. Yes?
Earth's pull on an object.
Okay. That's not bad. Let's go you.
So it's basically where so if you have a large amount of small balls compressed together, it'll pull in smaller balls that are just around its atmosphere.
Okay. I think, gravity is it's one of the mysteries we're still trying to solve if you guys are familiar with space-time the bending of space. I don't know much about it, but it's still one of the mysteries we're trying to solve. But we can simplify it. We don't have to worry about that mystery. We can think of gravity on Earth. You know, when I hold this guy here, and like there's something pulling it down. So we can really just think of gravity as a force that's pulling. Can anyone tell me what a force is? Yes.
A push or a pull.
Push or pull? I like that definition. Anyone else? Give an example of a force. Yes.
Something that acts on something else.
Okay. Can you give me an example?
Electrical force, like electrical current.
I want something I can touch. I want a physical example. Yes.
I want to take someone and push them off the cliff.
That's a good example. I like that. What else? I don't recommend doing that though. Yes.
Picking up something and throwing it. Putting force on it.
Okay. That's close to right. That's close. Yes.
Magnets.
So I want something very physical. I want to touch it. I want to be able to see it. Yes.
We use force to push things.
Great example. That's a great example. I have something here. Let's say it's my little desk, and I want to lift it up. I have to now apply some sort of force to it to make it counteract the force of gravity. That's exactly what it is. And at the end of the day, who here wants to be an engineer at some point? It's okay if you don't know. I didn't know what I wanted to be until last year. Who here wants to be a mathematician? Who here wants to be a computer scientist? Who here wants to understand the world? Everyone's hand should be up. That's why you guys are here. So, you know, to understand the world, we have to think about what the world really is, not just what we can read in a textbook. And I think a lot of the times what happens is we read a definition and we memorize it. So it's a good practice to sort of think about physical. I say, you know, I read the definition of a force. It's a push or pull. I think, what are some good examples of a push or pull? I go to the door, I pull the door. I can push it close. I can push my laptop close. I can lift it up. Take my glasses off. I can lift it up. I can lift it down. These are really physical examples that I think are important to sort of internalize. So that's good. So this is an example of a force. A very simplified version. You'll see this very often. Is a spring. You know, who here has played with springs at all? Cool. Good. Now, can anyone tell me what's happening here? Think about the fundamentals. Yes.
When it pulls against the spring, tension's being created.
Okay, I agree. And can anyone explain to me, you know, from the fundamentals that we talked about matter, you know, everything's made of these little balls. Yes.
The little balls in the spring are being stretched.
Yes. I like that. That's great. I think I already gave you a candy, but that's good. Yeah, you can have another one. That's a great example. So, like we said, forces are pushing and pulling. So, you know, in this picture, who can tell me what's happening in this picture? Yes.
Me?
Yeah.
Fingers are stretching the balls in the right.
Okay. And then, do you think I could say, what if I told, what's your name?
Charlotte?
Charlotte. I said, Charlotte, do you think the rubber band is pulling on your fingers in this picture?
Yeah.
Okay. Now, could I say, Charlotte, are my fingers pulling on the rubber band? It's the same thing. Equal and opposite reaction. You guys know Newton's 3 laws of motion?
Yeah.
Can anyone tell me what they are? At least one. Just one. Yes. Yeah.
Object tends to stay at rest or stay in motion unless acted upon by other force.
Okay. What does that mean? Because we all, I think, you know, most of us in this room would probably know that. But what does it mean? Yeah.
It means that without gravity in a vacuum, if you threw something,
Mm-hmm.
it would go on forever. But since we have vacuum and we have air resistance, if you threw something, it would get pulled down by gravity.
Mhm.
And it would stop because of friction, air resistance, or something.
I like that. So let's say I have a mouse. You guys all have a mouse, and you know, how is it? You know, let's say I slide it. Why does it slow down? Is there an external force acting on it? Yes. Friction. Who knows what friction is? That's okay. I didn't know what friction was till freshman year at MIT. So you guys know. What's friction? Can you give me a brief explanation? Either one of you guys.
Friction's kind of like a, I don't really know how to explain it, but it's something that happens when a object is slided or pushed across another object.
Okay, that's not bad. Can anyone else give me an example? Do you want to try? As soon as I bend this, it wants to snap back up. The table wants to snap back up on my hand, but I'm pushing down. And it's just like memory foam. If you guys ever play with memory foam mattress, you put your hand. Imagine the world with memory foam. Like when I stand on the ground, I'm deforming it just a little bit underneath my shoes. So this happens everywhere. It's important to keep in mind. So, begs the question, why is it that gravity is pushing on me? Why don't I just go straight through the floor into the ground? Yes.
Well, maybe it's because the floor has like more, the balls are more tightly compact.
Okay, I like that. I like that. What else? That's definitely correct. Yeah. Yes.
It's required to make you go through the floors more than the force of gravity.
Okay, that's also correct. But let's just think about in terms of the explanation we just gave. Yes.
So like Newton's third law, the ground is pushing back at you with the same force the ground is pushing you down.
Okay, so you're not going to move it up.
Yeah.
Exactly. So let's talk a little bit about light. So, how many of you guys think light is a bunch of balls, a bunch of particles? How many of you guys think it's a wave? Don't be shy. I want everyone to be shy. How many think it's a particle? How many think it's a wave? How many think it's both? Okay. So it's actually a particle and a wave. This is what's called wave-particle duality. And it's a very interesting concept in physics. So in this instance, we have a light similar to the light from a laser pointer that gets shot through a Coca-Cola bottle. And it kind of looks like a little ball that's traveling through it. But also it doesn't really look like a ball. It's something a little bit weird about it, a little funky. So if you guys are interested in this concept, I recommend looking up wave-particle duality. So we know that light reflects off of surfaces. How many of you guys have a mirror in your home? I should see everyone's answer. Yeah, I got a mirror now. Have you ever pointed to like a laser pointer at the wall, and then like you see it at the mirror, and you see it on some other part of the wall, and the cat goes crazy or the dog trying to grab it? So that's a function of the light reflecting off of it, and it does it off every object. Like the light that's coming in through this window is hitting the ceiling, it's hitting this table, and it's reflecting off of it, it's reflecting off me, it's reflecting off the wall and into my eyes. So we'll go ahead and watch this video load. So that's essentially, how light can reflect, and you can actually, this is some research done, I believe, at MIT actually. And it shows you how you can use the bouncing of light to see objects behind walls, which is kind of cool. So this begs the question, how do our eyes work? How do you our eyes need light. So how does that work exactly?
When you look at something, you see, your brain sees the object, the light reflects back at you.
So you're saying that it goes from my eyes to the object and back.
Yeah, the object goes to your eye.
Okay, the object goes, and how does that happen? Yes?
It is reflected off of that object, and the amount of light tells you what the colors are.
Yeah, exactly. So it hits the object, it hits my eyes, and that's how I'm able to see that. So now let's talk about energy. This is one of my favorite subjects. So, you guys are familiar with renewable energy. I'm a big fan. It beats alternative. So can anyone give me a definition of energy? I don't want a textbook definition. I want something like something real, something you can go ahead and tell your mom about if she's not a scientist, or your dad about if they're not a scientist or engineer. Yes.
Movement of the little balls.
Okay, that's not bad.
Something that you can use to do stuff.
Okay, I like that better. Did you have an example? Did you have an example? Yes.
It's something that makes things work or be able to move.
Okay, I like it, yeah.
The ability to use force.
Okay. Yeah, so I think, yeah,
Alright.
you should.
It's something that is able to move something, so like moving yourself or just something to move in general needs energy.
Yeah, so I would say it's the, yeah.
And like a universal force that causes everything to happen.
I would say that's a bit less of it. It's less of that. I think it's more. I would say it's in a general sense, it's like the ability to be able to do something. So if I wake up in the morning, I got a really good night's sleep, and I say, Mom, I got a lot of energy. I'm gonna go for a run today. My energy is I have enough that I can go for a run. I can do something. But if I wake up, I slept bad, my back hurts. I say, Mom, I can't go for a run today. I don't have enough energy. It's sort of like it's the ability to do something. So there's a lot of different kinds of energy. Can you guys tell me exactly what kind of types of energy there's pictured here? This one, this one. Take a guess. Yeah.
All of them have energy, just different types of them.
I'm sorry?
All of them have energy, just different types of them.
Okay. Yeah, so what types of energy is being displayed here? Mechanical? Okay.
First one has thermal energy, the second one has potential energy, and the third one has electrical energy.
Okay. Can anyone tell me, is there any other kind of energy going on in this one here?
Well, you said energy is the ability to do something that has the ability to you can use that to look up just about anything.
Okay, yeah. So maybe my definition was a bit too loose, but let's just stick to the scientific aspect of it. Yeah.
It's chemical energy too?
Yeah, that's a great one. Exactly. Yeah. So it's chemical energy. So I don't know if you guys know much about how batteries work, but they essentially are a chemical process that allows you to generate electricity. So we have thermal energy, which is heat. The cup of coffee is really hot. Gravitational energy, potential energy. When I'm really high up here, if I remove this track, I would just fall to the ground. And then chemical energy or electrical energy from here. So, how many guys, can anyone tell me what temperature or heat is? Yeah,
It's the motion of the little balls.
I like that. That's a good one. What kind of motion?
Just they stay within their own location, but they move back and forth.
Okay, yeah, I like that.
So rapid motion.
Rapid motion. Okay.
The vibration of them.
Okay, I like that.
So if the balls are moving very quickly, the temperature is a lot higher, but if they slow down, they're a lot cooler.
Yeah, I like that.
Or the little balls sitting against each other.
Yeah, so this is all correct. So we can think of heat or temperature as like these balls, and then let's say we're in a solid. Let's say I'm heating up this table or a pot. I'm heating up a pot and pan, and I have all these guys are really tight together, and I start heating them. They start wanting to boogie. They want to dance a little bit, and then their friend next to them says, "Hey, you're dancing. I want to start dancing too." So then he starts dancing, and then his friend starts dancing, and then it starts spreading over. Now you guys, whole pan is dancing. It's jiggling. That's what heat is, and that's how it spreads too. I'm wiggling. The guy next to me starts wiggling. That's how it spreads. So imagine I heat up the water that's here, just the water, and I put the water back in here. What's going to happen to the guys on the plastic? Yes.
The plastic is gonna heat up because the water balls are next to the dark balls, so they dance. They like that.
Okay. So if I looked just at the interface, I said, this is water, this is plastic. What's happening right at that corner? That intersection? Yeah.
Plastic starts to move.
And why does it start to move?
The water's moving.
Yeah. So the water guys say, oh, we're having a party, we're having a party. Oh, Mr. Plastic, come join us. So then Mr. Plastic starts jiggling. And then, but the thing is, because Mr. Plastic is made of a different kind of material, he's going to jiggle differently. It won't be the same kind of jiggle. It'll be a different kind. It may be less. Maybe the same. We don't know. But because it's a different kind of material, we know that it's going to change. So, can anyone tell me why, if this was super hot, I put my hand here, I go, ah, I can feel the heat. Why is that the case? Yeah.
Because since the moving balls in the jug like move against your hand, they also start to warm up too.
So, what happens to your hand exactly?
Um,
You have the explanation. Just what happens exactly to your hand?
like the balls inside it start moving.
Exactly.
So it
And your hand is, it stays the same. It doesn't want to, you don't want it to change at all. Did you have a question on that? Yeah.
Oh, I was just gonna say your hand, the ball doesn't burn a little bit.
Exactly.
And start vibrating or affects your nerves.
Exactly. So why is it if we heat water up so much, it starts to steam? Based off what we learned. Someone who has an answer. Yes.
The little girls that get from dancing so much that they start like turning into a gas.
Well, so you went from a great fundamental definition, and then you started talking about something a bit more complicated. So let's work with that fundamental definition. So they start dancing so much. What happens? Good.
But they can't stay like that when flying.
Okay. Very close. Very close. Yeah.
They get very jumpy and leave.
Yeah. Remember, they're connected, but they can also get disconnected. So if they're moving around so much, they're jiggling around so much, they get ejected. It changes phase. It becomes a gas. So think about it. We started off with this definition of matter as this gas, of matter as these little balls, and from that we're able to sort of think about why this thing gives off vapor as a gas. It's kind of cool. That's a little gif of how these guys are jiggling and say, hey buddy, let's go party. They start jiggling too. And all of this, it may seem kind of like very touchy-feely, but all of this actually has a very rigorous mathematical background for it. If you're ever interested in the subject, there's a lot of really neat mathematics that goes into understanding how this guy says, oh, I'm jiggling, and then he wants to transfer to his partner, oh, I'm jiggling. It's really, really neat. I'd recommend, if you guys are interested, feel free to come ask me afterwards. So, the question is now, why do we shiver when we're cold? Someone who has an answer. Yes?
The little walls in our skin and everywhere else want to get warmer, and to do that, we shiver, which makes them.
Exactly. Can the cross. Yeah, so that's exactly it. So now we're going to talk about a pretty cool sort of consequence of everything that we've learned, which is fire. How many of you guys have made fire before? How many of you guys have made fire and your parents knew about it? How many didn't know about it? Because I remember I used to make fire. That's besides the point. So fire is, when you burn fire, what happens? You have a lot of light, but is there anything else that's emitted from the fire? Yeah.
You generate a fuel source, oxygen, and
Okay, but what's emitted when I make fire?
carbon dioxide.
Carbon dioxide. Carbon dioxide is emitted. Carbon dioxide is a mixture of what? Two things. Yes.
Two different types of balls.
Okay. And what are those two balls?
Carbon and oxygen.
Great. So it's carbon and oxygen. Where can we find carbon in the world? It's a good place to find carbon.
Anything that's alive.
Okay. Let's say I wanted to use it for fuel. What's another good place to find? Here.
Trees.
Trees. Exactly. Trees are a great place for carbon. They have a lot of it in it. Where's a good place to find oxygen? The air. Does anyone know the percentage of oxygen in the air?
It's 20 something. It's mostly nitrogen.
24.
That's probably right. I think it's around there. Yeah. It's pretty good. It's a pretty sizable amount. I think the largest source may be in our oceans, actually. But for the sake of it, let's say in the air. So we have all this carbon in our trees. We have all this oxygen in the air. And fire results in carbon dioxide. So why don't we have trees? Why aren't the trees on fire? Why don't this carbon and oxygen react to produce heat, which makes a flame, and then you get carbon dioxide? Yeah.
Because fire also needs like a catalyst.
Exactly.
So it would need a lot of heat.
It needs an energy input, which is what this guy's doing over here. He's putting energy in. What kind of energy is this? Thermal, but he uses friction to generate it. Exactly. So he applies a little bit of energy. It causes these oxygen and carbon molecules, or balls that are in the air, to then snap together. Do you guys know what happens when two molecules come together? Do you know what happens? Anyone?
A chemical reaction.
To some degree, yeah.
They release heat.
It releases heat. That heat is known as a fire. Right? So you may ask, so this is the result of it, it's a fire. So then you may ask, where does this, so someone may say, oh, Sina, I thought energy is neither created or destroyed, and you're telling me if I have oxygen and carbon, I can just make this energy. This is essentially energy. Then the question is, where does this energy come from? What's the biggest source of energy for the world? Yeah,
Sun.
the sun. The sun. How does the sun power this reaction here? Yeah,
Well, it helps to grow trees which produce the carbon.
great. What do we inhale as humans? We want oxygen. What do we exhale? Carbon dioxide. What do trees take in? Carbon dioxide. What happens when we burn them? CO2. So it's a cycle. It's a cycle. We get energy from the sun, produces a tree, which takes carbon from the air, because we breathe it out. It stores it in its in the wood of the tree. And then we have so much oxygen, but when we bring the two back together, it releases energy that it got from the sun. So essentially, like, energy from the sun is a fire. Isn't that kind of cool? When you look at a fire, you can think, this came from the sun, pretty much. It's kind of interesting. So that's more or less it. Thank you guys for paying attention. If you have any questions, I'd be happy to